All right, so this is chapter 4, our trig identities. And so we should start by talking about what an identity is. So these are things where we take an equation, we take something that's true, and we do transformations on it. So we take an equality, we do something to one side, do the same thing to another side, and we come up with different representations of the same thing. So these algebraic transformations allow us to have different identities for different purposes. The one that we start with is called the Pythagorean identity. All right, so if we imagine a unit circle, this is our Pythagorean identity. You guys have seen this in a couple of problems in the book, but it says sine squared x plus cosine squared x equals 1. And this one has a good geometric interpretation. So if I was to draw my unit circle and label my pieces, so I have a radius, and what's the distance, what's the radius going to be? 1, because it's my unit circle. And then I have my coordinates. All right, u and v. And from the Pythagorean theorem, what do I know to be true? Yeah, u squared plus v squared equals 1 squared, right? A squared plus b squared equals c squared. So that's true, but we've also defined u and v on our unit circle as some trig values. What does u stand for? Cosine, and v is sine, right? So we have this relationship, and just by substitution, where I see the u, I can put cosine. Where I see the v, I can put sine. I come up with my Pythagorean identity. So cosine squared x plus sine squared x equals 1. Now, key notation difference here is if I have cosine squared x, that means cosine x times cosine x. Is that the same as if the exponent was on the x? It's not. Okay? So be careful. That's another common mistake with this. This squared on the cosine means cosine x times cosine x. Not the same thing as cosine of x squared. All right. And what mode does your calculator have to be in for this to work? Or which one do you think? Does it matter? It shouldn't matter. So these trig identities, if we're talking about transformations, things that are equal, it should work for radians or degrees. And so this, the way I had the picture drawn, looks like it's radian measures, but with the x. But it should work for degrees as well. So these things are always true. That's why we can prove them. If something is always true, we can get a proof attached to it. All right, so we have a couple of variations on the Pythagorean identity. And we do some transformations to get different looks at the same thing. So if I start with my Pythagorean identity, and I divide everything by cosine squared x. So I get cosine squared x over cosine squared x, sine squared x over cosine squared x, and 1 over cosine squared x. So I haven't done anything. I have a division property of equality. I can divide by the same thing on both sides and still be equal. But now I have some different, I can simplify a little bit. So cosine squared x over cosine squared x is what number? 1. Sine squared x over cosine squared x, that's another trig function. It's tangent squared x, and 1 over cosine squared x is secant squared x. So I get 1 plus tangent squared x is secant squared x. So that's my first variation on the Pythagorean identity. Well, I could also divide by sine squared x. So I take the Pythagorean identity, I divide it by sine squared x, and I simplify. Cosine squared x over sine squared x is cotangent. All right, it's 1 over tangent. Sine squared over sine squared is 1, and 1 over sine squared is cosecant. So there's another variation on the Pythagorean identity. What's the last thing that I could divide by? I can divide by 1. Right? But that's not going to change anything. So I have those 3 variations on the Pythagorean identity, and we want to talk about our domain and our range here, specifically our domain. For the first one, is there anything that's going to make my calculator unhappy if I plug it in? Let me think. Well, it's the same range for sine and cosine, right? I can put in anything I want. I'm talking about angles or radian measures, so I can put in anything I want. I have no restrictions on it. And so the way that that's going to look is all real numbers. And this is a script R that sometimes you'll see in the book, which stands for the set of all real numbers. So I can put in whatever I want. Compared to this one. So when I divide by both sides by the same thing, there's only one number that would make my calculator blow up. What's that number? 0. So when cosine squared is 0, I have an error here. So my domain is everything except where cosine squared x is 0. And that's where x is pi over 2 plus any rotation of 180 degrees. So 90 degrees, right, 270, any rotation from there. So that's where I'm going to have a domain error because I'm telling it to divide by 0. All right, and the third one, what's my problem going to be? Not when cosine is 0, but when sine is 0. All right, so I can't have sine equal to 0. And where is sine equal to 0? Is it the same as cosine? No, it's at 0 and 180, or 0 plus pi m. So we have restrictions on our domains. All right, and it's just because we can't divide by 0. It's nothing weird, but it's just our algebraic property. We have an undefined value when we divide by 0. All right, thumbs up if you're with me so far. We've taken the Pythagorean theorem and we just made it look different 3 different times. Okay, what you're going to see more often is something like this. So prove that tangent x times quantity cotangent x plus tangent x equals secant squared x. This is the bulk of the first part of the chapter. And it might look overwhelming, it might not. But there's kind of a method of what we want to do to attack this. So you're going to see on my papers I have LHS and RHS, which is just the left-hand side and the right-hand side. And my goal is to take one of these sides and algebraically turn it into the other side. That's going to stand as my proof. Okay? So in general, too, I want to start with the more complicated side. Because if I start with secant squared x, well, there's only so much I can do with that. But what's the first thing I could see to do with this side over here if I wanted to transform it? Somebody said it. Did you?
If you multiply if you distribute it, you get 1 plus 1 squared.
Yeah. If I can distribute right away and make that simpler. So I'm going to start with that side. So I'm going to start with the left-hand side and try to turn it into the right-hand side. Now you could always start with the right-hand side, but it sometimes is going to be easier to have more complicated in making it simpler as opposed to the other way. All right. So our goal is to start with the left-hand side and transform it into the right-hand side. So there's my left-hand side, and just like Gina said, I'm going to distribute that tangent through. So I get tangent times cotangent plus tangent squared x. Well, cotangent is 1 over tangent, right? And I still have tangent squared x, and tangent times 1 over tangent is 1. So I get 1 plus tangent squared x. And what does that equal to from one of our Pythagorean identities? Secant squared x. So but let's say you didn't remember that. So this would serve as a proof at this point because we've already derived another identity. Yes?
So if we found it, we know that 1 plus tangent squared x is secant squared
Yep.
x. This is one of our identities. So if we were writing a proof, could we just write that? Should we say, oh, this is one of the identities, that's why it's correct?
Exactly.
Okay.
So that's the power of proving something, is once you've proven it, you can use it, right? So if you prove all the angles in a triangle add to 180, well, now you can use that fact anywhere down the road. So once we have that this equals secant squared x, we would be able to just assume, we would be able to state that it's equal to secant squared x. You might not remember that. I have a hard time remembering all of the identities and what they do, and for me it's easier to try to break it down, because we can continue to look at this. So you could state it right there, we've equaled the right-hand side, or I could try to expand this. So let's say I forgot that this equals secant x. Well, tangent squared x is sine squared x over cosine squared x. If I wanted to add these two together, I need to get a fraction here. What's my denominator going to be? Cosine squared x. So I get cosine squared x plus sine squared x over cosine squared x. And this is my Pythagorean identity. What does that equal to? Everybody say 1. 1, thank you. All right. 1 over cosine squared x is defined as secant squared x. So it depends what you want to do. You can remember more identities and use them for sure, but you can always break it down into kind of the basic ones. And one of the basic ones is our Pythagorean identity. So this is my proof. You're going to see in the book QED, it's Latin for quaderat demonstratum. You can see on a lot of proofs. All it means is it's been shown. So it's a line at the end of the proof that says you've demonstrated what you set out to demonstrate. We've shown that the left-hand side equals the right-hand side. We've proven that is an identity. It works for all angles. So let's go back to the daily 2 problem asking, is a graph going to serve as a proof? So if you graph this side and that side, they would coincide exactly. But is that a proof? Does the graph go on infinitely far for all numbers of x? It does. Can we show that in a window, though? We can't. All right. So if we had a window that went infinitely long, we could say that a proof was a graph was a proof. It doesn't work though because we need a general case. This is a general case for any x we can get from one side to the other. So a graph can disprove something. If the graphs don't correspond, then it's not going to work. But you can't prove it with the graph. All right. Your turn. 2 to prove. So one that's a little bit easier and one that's a little bit harder. So again, you're going to define your left-hand side, your right-hand side. You're going to pick a side that you want to start with, and you're going to transform it into the other. Now, on the first one, I would start with the left-hand side. It's more complicated. And I would definitely start with the left-hand side on this one because it takes a very bright mind to be able to turn 13 into that mess. Okay, so start with the more complicated side, break it down, see what you can do, and then we'll talk about it in a couple minutes. Talk with those around you. I'll come and help as well.